Okay, so we've got a Markov chain and we're interested in representing the sort of the probability of going from one state to another. So we've got a discrete time Markov chain. It's discrete time because we've got discrete time steps, and also we've got a discrete random variable that we measure at each time step, which we has states. We'll start with the transition matrix. The transition matrix, which we denote by P, of a discrete time homogeneous Markov chain, is going to be if there's k states, it's going to be a k times k matrix, such that we're going to have that the ijth element, so the observation, the value on the ith row and the jth column, which we'll denote as Pij, is the probability that in a single time step, so let's assume I'm time step n, in the next one I will go from ai to j. So if I'm in for example, the second row and the third column, that will be the probability in one time step of going from state 2 to state 3 in one time step. Let's illustrate this with an example. We've got a gambler, and they start with $1, and basically they're going to keep playing until they either run out of money or they get to $5. And they play a game that each time they have a probability P of winning, and they get whatever money they bet. And we've got a simple system. If basically our winnings are such that when we win, we're still less than 5, we're going to bet everything. Otherwise, we're going to bet the amount that we need to make $5. So let's have a look at the state diagram. So here's where the gambler starts at state 1. And first of all, the rules are that at state 1, they're going to either gamble at everything, and if they lose it, they go to 0, and they basically stick at that point. That's what we call an absorbing state because they've run out of money. If they win, they've now got 2. 2, they still can't get to 5 in just one go, so they bet everything. If they lose it, well, if we lose it, we go straight down here. But if we win, we go to 4. With 4, we only need to now bet $1 to get to 5. So we either bet that $1 and win, and we get to 5, and we stop the game, or we lose it, we go down to 3. Once we get to 3, we're going to bet 2. So we either bet 2 and we win, or we go down to 1, and then we circle around. So there's our state diagram. Let's now represent this as a transition matrix. And here it is. We're going to label this to make it nice and easy for us. So this is state 0, 1, 2, 3, 4, 5. And this is 0, 1, 2, 3, 4, 5. So for example, we saw before, let's have an example 1, we have a probability P of going up to 2, or the other possibility is we go down to 0. So if we're in 1 here, we've got probability P of going up to 2, or 1 minus P of going down to 0. And see, the entry of this tells you how I go from example 3 to 1. So you're basically going from the state on the row to the state on the column. Well, let's now think of another thing. I don't want to maybe look in just one step. I could do that quite easy. I don't need a matrix. But maybe I want to work out what's the probability I go from $1 to winning in 10 steps. So we're going to have a new transition matrix, and we're going to call this our M step. I'm going to illustrate that by now putting our P, and then in the subscript, so the superscript, we have a bracket M. And this now, the entries of this are going to be the probability of going from state I to state J in M steps. So now the numbers are not the probability of going in a single step, the probability of going in M steps. So we need a quick way of actually working out this. How can I actually get all these values? Well, the nice thing is we've got this beautiful little theorem. It basically says my M step transition matrix I can get by taking my single step transition matrix and multiply it using matrix multiplication, multiply it by itself M times. If you're interested in why that's true, it uses proof of induction, and I've put that in the handout for you. So have a look at that. So let's have a look at an example. We've got this one where we have basically, in this case, 3 states. Let's call them 1, 2, 3. And we've got 1, 2, 3. And I want to work out what's the probability we go from state 1 to state 2 in 3 steps. Well, how do we do that? Well, what we do first of all is we take our P and we cube it, and then we are going to go and look at the 1, 2 entry. So let's do it. Here's my code. First of all, we've got this code here, and all this does is it creates me a 3 by 3 matrix. A couple of things. I give all my numbers as a single vector. Then I say I want 3 columns, and I say order these by row first. So here's my 3 by 3 matrix. And now I just have to multiply it. Just so you know, to multiply, do a matrix multiplication, in R we use this percent times percent. And again, percent times percent. So I've done it 3 times. And then finally I say, give me the entry in 1, 2. And that gives us this 0.40625. Well, next we'd like to say, well, what's my starting point? So I'm going to have some new notation. We're going to have a thing called P0. And that is going to be a row vector, where the first entry will be the probability at time 0, I'm in state 0. The next one will be the probability at time 0, I'm in state 1, etc. So it's going to be a vector, obviously all the entries add up to 1, that tells you the probability I'm in each state at time 0. And if I want to work out the probability of where I will be in the states at time n, I just take my single step transition matrix, I multiply it by itself n times, and then I pre-multiply by the probability at time 0. Again, in the handout I've given some derivations of that. This is really nice. It's very easy to put this into a computer and just run it and get your probabilities. Okay, that's it. We've done 1 step and m step transition probabilities and shown how, if we know where we start, we can work out where we will be, or probably be, in n steps. See you next time.